What's up, everybody? I have a new paper up. Most mass-dependent isotope fractionation is due to cell evolution. Here's the beginning of the paper. I don't know if you guys can see that. I'll read it out, some of it for you. Isotope fractionation means the separation of specific isotopes of a specific element. Say O17, which is an isotope of oxygen, is heavier than O16, so it will sink easier into a star because it is heavier. This is mass-dependent isotope fractionation. Most isotope fractionation taught by mainstream only include mass-independent fractionation. That means there's no mass isn't important. It's independent of the isotopes separating themselves. And that being said, I have here a little diagram. You guys can read this. Mass-dependent fractionation due to mass loss. So this is an exaggeration of the graph of what I think happens here. But if you want to read along with me by opening up the Vixra page, I'll link it to the bottom. On the left-hand side, I have the sun's deuterium and hydrogen, both those isotopes together, and I have a similar star right next to it. The hydrogen takes up a lot more. You can see that, and then the bottom, that little bit is deuterium, and then you have red dwarfs. Then it moves down to Jupiters, and then gray dwarfs, Neptunes, ocean worlds, and the Earths. And of course, all the water isn't deuterium like I have down there. It's just an exaggeration to show as the star gets older, it loses more and more. It loses more and more of the lighter isotopes, and the heavier isotopes fall towards the center of the star. And that's very important to understand because the establishment, they don't have stars as being young planets, and their isotope fractionation examples, and I talked to Daniel Archer about this. They try to interpret all the data before they even let all the data be shown. So they have all these measurements of all the isotope differences in a whole bunch of different solar system bodies, and then they mumble jumble it all up into a giant research paper that's like 60 pages long. And there's not a single graph in there that says, okay, these are the percentages here, these are percentages here, these are percentages here. They're always trying to reinterpret it in ways that they already think is happening without actually just looking at the data and making it incredibly difficult to find where the actual percentages are. So say you have this much deuterium and this much hydrogen, and then here's the percentage. It's not that clear cut. They do models, and then they say, well, it's supposed to be like this, and then it's supposed to be like this, and you have to dig through all this stuff. But anyways, here's the paper. I'll link it to the bottom. And I just wrote up a new paper here. It's pretty straightforward. I know that all this talk about Ultima Thule is happening, about, visiting the most distant object in the solar system. And of course, it's one hell of a feat. I couldn't do it. I couldn't send a satellite up there and have the patience to wait and, do all the electronics and engineering that goes behind that. That's far beyond my capacity. My capacity and my skills are limited to understanding what that damn thing is. And it's not two rocks that clump together in outer space, even though it looks like that. What it actually is, and the Vixra paper is yet to be uploaded, is it's the remains of an impact. So here's the impact area. So you have two objects like 300 miles and 280 miles wide. They impact each other, and it's just like a water droplet splash. The splashing material exits out the side, and a lot of it ends up being a single object, or if it has a little bit of angular momentum, say it's that little drop or that bunch of rock is spinning just slightly, it will start forming two lobes, and it will go like this. It will stretch outwards a little bit, and as it spins, it'll start solidifying. That's why Ultima Thule has two lobes to it. It's not very difficult to understand. But the NASA and all the experts, they say, well, it was a bunch of icy particles that clumped together. And I'm like, well, what heated up the objects to get them to melt down together? How did they lose the angular momentum? Because you just can't clump material. The rocks just don't self-assemble in outer space. You need something to heat the material up. You need something to collect it together. You need something to make sure there's no heat loss. Because if you heat objects up, how do you prevent the heat loss? And how'd you heat them up in the first place? The damn thing is 42, 43, 44 AU away. That's like, what, 4 billion miles? It's far, far, far away from the sun. What was heating that object up? But, you know, NASA, they don't want to give you a straight answer. Anyways, that being said, I'll link this to the bottom when the paper comes up. It's very simple to understand. And if you want to understand like how asteroids and comets are made, just look up collision videos of water, and you'll see that's exactly how they're made. And water is a good example because the asteroids that collide with each other, they're traveling at 15 miles a second. That is insanely fast. There's no way two objects clumping together in outer space are going to leave a larger object. If anything, two objects colliding in outer space will leave a lot of shrapnel. There be very little left, a lot of space dust, and a lot of asteroids, a lot of soon-to-be meteors that then enter into the atmospheres of younger, hotter stars. But all right, you guys, today is January 5th, 2019. I hope this gives people some options to consider. And also keep in mind, like when astronomers, when they have their consensus, they don't have any alternative. That's a big red flag. When you don't have alternative explanations for stuff, it's like, this is how it is, to hell with everything else. That's a big red flag, and that's what you should watch out for. All right, y'all, later.